So hello everyone. Hello everyone. This is Jungwon Kim. So we're gonna start the English class for reinforcement learning today. So I'm so sorry for late login today. So we will gonna have some makeup class soon. So I will make a schedule for the other part. Okay. So clean PowerPoint. What does that mean by clean PowerPoint? I understand. I understand what you are talking about. So then I will make the so I forgot to make a clean PowerPoint yet. So I would like to make the clean PowerPoint maybe tonight or tomorrow morning. Okay. So then I will distribute the PowerPoint in our chatting room or a Blackboard. I will do that. Okay. I'm so sorry about that. So let me download the slide at first. Then let me start the class today. Okay. So okay. Let me show you. So not this one. So where's the slide? Where the slide? Slide. So let me find the slide. Okay. Do you have it? Then you can send me over chatting box or chatting room. So let me find the slide first. Oh, thank you, Lewis. So let's do the lecture with this slide at first. Okay. Where's that? Here. Where's that? Here it is. Okay. First of all, thank you very much for your attention and participation, and thank you very much for your time today. So today, last time I told you that I would like to upload the English lecture for reinforcement learning at the time, but I was lack of some time nowadays, so I was so busy. That's why I thought that it would be better to have English class during this lecture, during this on-time classes. So I have a plan to make a presentation only in English. That's why this lecture is only for international students. For international students, I would like to make an English class as much as possible. And I would like to have some makeup class for this topic, okay? But we can make a schedule maybe in the end of this, in the end of the lecture today. So here I would like to focus on the reinforcement learning. So today we will go through the introduction to reinforcement learning, and we're gonna do some exercise with basic steps of the reinforcement learning, that is Q learning and Markov decision processes. In addition to that, we will gonna have some lecture about deep reinforcement learning, that is the reinforcement learning with the deep neural network architecture. So it's not same with the previous ones, okay? So in our undergraduate materials in industrial engineering department or mathematics department, so we have some idea about Markov decision process, Markov chain, or something like that. So, but modern reinforcement learning is quite different from the others. That's why we have new idea that is called deep reinforcement learning. So we will gonna study about this one as well. And then in addition to that, I wanna let you know how to do some basic implementation with the Python. And then lastly, I would like to make a brief introduction to imitation learning. So these topics are all we have to do today. So first of all, let me briefly introduce the history of reinforcement learning. It is quite old. So 1954, Professor Marvin Minsky at MIT received his PhD from MIT. So his dissertation title was Stochastic Neural Analog Reinforcement Computer, which means that the basic concept of reinforcement learning was established at the time. So it is much more older than neural network architecture. That's why it might be one of the oldest topic in machine learning. Okay, the reinforcement learning is analogies with animal learning and psychology. And one of the most successful application in reinforcement learning is job shop scheduling for NASA space mission. So in NASA, they have some unmanned aircraft, unmanned missile, or unmanned space craft, and the flight is flying in the universe, and while they are flying, they have to take a lot of pictures in galaxy. That's why they have to go through by the some planets, then they have to take the picture. That's why we have to do some trajectory optimization. So that was fundamentally based on the reinforcement learning at the time. That's why we are saying that NASA space mission is one of the successful application in reinforcement learning. So when I was undergraduate students, we have a lot of undergraduate programming clubs. Those are working for robot soccer. So robot soccer application is also one of the most important application in reinforcement learning. So I was a university student from 1999. So it is just 1 year before my university life. That's why I remember that most of my senior students at Korea University had joined the club for robot soccer. So we can see a lot of programming with reinforcement learning at the time. So reinforcement learning was quite old and quite widely studied for a long time. Then, but we all know that reinforcement learning cannot be used to any kinds of application. So there is one specific application that can use reinforcement learning. So we have to ask when the reinforcement learning can be used. Then if we want to find the approximate optimal action sequences for expected reward maximization, then we can use the reinforcement learning. Here, our main focus is the sequence. That means that we are not doing only one single action. We have a sequence of the actions, then we can use the reinforcement learning, okay? In addition to that, we have to define the action and reward, then everything is okay, because we have some quite well-established formula that can be used in many applications, okay? So action sequences, we have to define the action sequences, right? That is also called policy in reinforcement learning. So we have action sequences, that's why we have trajectory optimization, okay? So the arm, we have the arm, so it has the action. The robot arm has the action, right? In order to make a delicious food, then we have some trajectories about that. Then this is the sequence of the actions. That's why we need reinforcement learning. In right-hand side below, you can see the application about the robot soccer. That is also has the sequence of the actions in order to do the playing the soccer. That's why it is also an application of the reinforcement learning. So simply saying, if you want to make an action sequence for achieving your goal, then you are using the reinforcement learning, okay? But in classification task, you have to make a classification only one time. You have to make a classification for the other applications. That action is only for one time. But here, this is the sequence of the actions, okay? That is the main difference is here, okay? So in reinforcement learning, there is one agent. So the object which is working with the reinforcement learning is called object, is called agent. So this is the agent, okay? This is the agent, and the agent is living in an environment. Okay? So this one will take an action, this will take the reward, and then this will have the updated state. So this is quite simple, but this is quite simple, but this is not clear at this moment. That's why I would like to give you one more example about this one, okay? So this is the reinforcement learning setting. The general reinforcement learning problem is formulated as a discrete time stochastic control process. This is quite complicated graduate level terms that is hard to understand, but you can understand this term based on this illustration. Suppose that you are an agent, reinforcement learning agent. This is living in the environment. So in an environment, you are observing some state, you are taking on action based on the reward. And then when this one taking on action, this one move to the other state and so forth. So here the agent start in a given state within its environment by gathering initial observation that is called omega, okay? And then every single time step, the agent has to take an action, but the action should be based on the reward. Suppose that I can take the action in the given set, 4 different given set. So for example, I can move forward, I can move back, I can move left, I can move right. We have 4 different actions. Among these given 4, you have to take one, which can give you the maximum reward. Okay, that is your action, optimal action in reinforcement learning. So you have to obtain a reward which is maximum, then you can take the action, right? And then by taking the action, you will update your state and so forth. This is the reinforcement learning setting. So let me give you one examples about that. So here you have to understand what is the dynamic programming, what is the others, and so forth. But here, explaining dynamic programming takes a lot of time, and it is fundamental stuffs in algorithm design. That's why we're gonna take 4 or 5 classes in order to understand what is the dynamic programming. But at least you have to remember that this is fundamentally based on the recurrence. So in recurrence, so let me give you what is the recurrence here. So here, this one is recurrence, okay? I will explain this one, we will move back, okay? So here, in recurrence, this is recurrence. Suppose that you wanna calculate 3 factorial. In order to calculate the 3 factorial, you have to put 3 inside this function. So in x, you have 3, but x is not 1. That's why you have to go to the first if, and then this is the first one. And 3 multiplication f of 3 minus 1, that is the 2. That's why you have this result, okay? And then you have to find the 3 f of 2. That's why you have to put 2 this one again. So in this case, you can realize that in order to solve the recurrence problem, then in order to solve this one, you have to call this function itself again inside there. So in order to solve this one, you have to look at this one again and again. This one is calling again and again. This is called recurrence. So here, the dynamic programming is used for this problem because in dynamic programming, you suppose that you have n-size problem, you will gonna solve this one in a smallest size at first, and you will increase the size more and more and more and more. That's why in order to solve this large scale problem, you are doing the calling your function itself again and again. That's why the basic formula of the dynamic programming is almost similar to recurrence, right? That's why dynamic programming is fundamentally based on the recurrence. Based on this concept, you have to understand the complexity of the dynamic programming. So dynamic programming's computational complexity is quite heavy. So in dynamic programming, if you want to use the dynamic programming, it takes a lot of computation. It is not polynomial time. It takes a lot of time. That's why you need some approximation algorithm, which can accelerate the computation for the dynamic programming, okay? So that's why we are mentioning dynamic programming here. So this is not, so here we have one example about the dynamic programming that is called the Fibonacci number. In Fibonacci number, suppose that you want to calculate this number, okay? 1, 2, 3, 4, 5, 6, 7, 8. You want to calculate F8. Then what is the F8? In order to calculate F8, you need F6 and F7 because A minus 2, A minus 1. You have F6 and F7. Then F6 can be solved by F4 plus F5 and so forth. That's why the Fibonacci function cannot obtain the result immediately. They have to call itself again and again. That's why this is also one example about the dynamic programming or recurrence, okay? So the other application is the Pascal's triangle. So in this case, when you look at the Pascal's triangle, suppose that you want to calculate this number, you want to obtain this number. This number can be obtained by the addition of this one and this one. Then in order to obtain this one, you have to know this one and this one, then you can calculate this one. In order to understand what is this, then you need this number and this number. In order to understand what is this number, then you need this number and this number and so forth. That's why in order to get exact value of your desired value, you have to call yourself again and again. That's why this is also called recurrence. Also, this is fundamentally based on the dynamic programming, okay? And similarly, knapsack problem also fundamentally based on the dynamic programming, but it's quite complicated problem. That's why let me skip what is the knapsack here, okay? So just for the formula, you can see that In order to calculate this function, you need this function inside there. That's why when you look at this one, within the OPT, you have to call OPT again. In order to solve the OPT, then you have to call inside again and again. That's why this is also called recurrence. So in reinforcement learning, the formula is similar to the recurrence. It's exactly same with the recurrence. That's why you need dynamic programming like solution procedure. You understand that? Then here, now you are here. You wanna do the Q running, which is the most simplest type of the reinforcement learning. So this is quite dirty, but let me explain here. So pink here. Suppose that you are a robot here, and then you cannot go left, you cannot go up. So left and up, those are all 0. If this one goes to the right hand side, you will get 0.5. If this one go down, you will get 0.3. Right 0.5, down 0.3. That's why this is the maximum. That's why you have to go to the right. That is the action in that state here. So this is a robot. This will look at where it is. This will look at what is the action they can choose, and then they will gonna take one action which can guarantee the maximum reward. Here you have two types of reward, 0.3, 0.5. That's why you have to go to the right hand side. Okay, so you have to take the maximum reward. The Q function here is called reward. That's why Q running works based on the reward. Okay, so fundamentally here, suppose that you are in S. Then this one go to the S prime. So S prime is the next times last state. So this can go to S prime by taking on action A. But this is not free. In order to take on action A, you have to get reward. So this is the reward what this agent get. That's why suppose that the reward here S with action A, you will take the reward R at first, and then this one will go further and further and further. That's why, but in addition to that, the action taking will guarantee the maximum reward receiving. That's why you will take the maximum action for the other procedures, right? So this is the formula, basic formula for the Q running and reinforcement learning. When you look at this one carefully, you see that in order to calculate the Q, inside there, you have another Q. That's why that is very similar to the recurrence, right? That's why our formula is very similar to recurrence. But here, let me emphasize again that solving recurrence takes a lot of computation. It's not polynomial time. That's why if the states are small, problem size is very small, you just use this one and that's it. In addition to that, dynamic programming can guarantee the optimal solution. That's why if your problem size is very small, then please use these kinds of the recurrence. And that's it, because it will guarantee the optimal solution, but it takes some time. On the other hand, suppose that your problem size is very big, then the computation becomes bigger and bigger. Then it's very hard to get optimal solution in a given time. Then what we can do? Then we can use a neural network in order to calculate the reinforcement learning solution in a faster manner. That's why in conventional or old type of the reinforcement learning, you use Q running that is not fundamentally based on the neural network. However, it can guarantee the optimal solution based on the recurrence. And then you can, even though it takes some time, if your state size is very small, then it's very good because it can guarantee the optimal solution. Okay. So here you can see that, okay, this is fundamentally based on the recurrence, and then this can be solved by the dynamic programming, and then you can guarantee optimal, which is very good, but the computation is heavy. That's why it cannot guarantee polynomial time computation. That's why you need some time to get the optimal solution. That is the main thing what I want to say here in this slide. Okay. So this one shows one example how to use the Q running. This is very famous application. You may saw this one a lot in YouTube or lectures and so forth, because this is very famous example, which is called the frozen lake. In frozen lake example, let me say that you are agent here, you want to go to the goal, right? And then you have to move one step further and further. You want to go to the goal with your given equation. Only one, this one, okay? And this agent can move up, move left, move down, move right. It has 4 different actions. That's why the action taking is based on the reward. That's why 4 different spaces, 4 different reward values. That's why individual segment space can be divided by 4 in order to put different reward values in each segmentation, right? So suppose that you are here, you want to go to the right-hand side from S sub 0 and S sub 1. Initially, all the reward values are set to 0, and then you want to make this agent come to goal. That's why this one reward R value becomes 1. So S sub 15, which is the space of the goal, and left means left-hand side. So this becomes 1. This does not need to be 1 because this type of the incoming is not possible because of this wall. And this is not possible. This is not possible. Only coming with this direction is available. That's why here, only this one is 1. The others does not need to be 1, okay? So in S sub 15, only left side reward becomes 1, and the other values are all 0. And Q values are all 0 initially, okay? Now it starts with the 1. Suppose that your robot agent is located here. It can go down, it can go right-hand side. Then suppose that you choose the right-hand side as a 1. So the equation is here. You want to go to S sub 1 from S sub 0. Then, as you can see here, you are going to the right-hand side. So suppose that you are in S sub 0, you want to go to the right-hand side. Then, by going to the right-hand side from S sub 0, by taking A sub R, then you will earn the reward value R. And then here you have 4 different Q values. So you have 4 different Q values because you have 4 different actions. Then this R value is 0 because only this one is 1, the others are all 0. And initially all the Q values are 0 as well. That's why these are all zeros as well. That's why you have 0 plus zeros. That's why your return value is 0. Okay. So you have no updates. That's why you have no preference here. That's why you take the random action again and again. And finally, suppose that you arrived here, number 2. You arrived here, number 2. And now you are in S sub 14 here. You want to go to the S sub 15. Now you are in S sub 14. You want to go to S sub 15. And then you are in S sub 14 and go to the right-hand side. By going to this one, you will take this reward. So you will take the reward here, this formula, and take the 1 here and max the Q. But these Q values are all 0. There is no need to be updated. That's why these are all 0. But here you have a 1 plus 0. That's why the result is 1, which means that this Q value becomes 1. This becomes 1, right? And then you are starting from the starting point again. And when you go walk around nearby here, suppose that you arrive here and you are in number 3. If you are in number 3, suppose that you are in number 13 here, and then you want to go to number 14. And then suppose that you are in S sub 14, you want to go to number 14 by taking the action of the right-hand side. So you have A sub R here. By taking this one, the small r is always 0 because there's no need to be updated R. That's why R values are all 0 except this one. That's why you take the 0 at first, and then you take the maximum Q. This Q value is 0, this Q value is 0, this Q value is 0, but lastly, this one is 1. That's why when you 1, it becomes 1. And then when you calculate this one, you have 0 plus 1. That's why this is also updated to the 1, which means that this one is updated to 1 at first. This one is updated for the next round. For the other round, if the agent is nearby here, then by taking the Q value among this given by taking the Q value among these given 4, then this one becomes 1. So if your agent is nearby 1 state, then your Q value is updated and so forth. And finally, you see that this is updated to 1, 1, 1, 1, 1, 1, 1, 1. All the passes are updated, and finally, when you update in your starting point, you follow the 1. So you follow this pass, then you can get this pass. So you can find your path in a given state, okay? But here you can realize that this is not optimal because the path becomes just like that. But in here, you can see that you are doing some detouring in this space. Then you have to think why this one's detouring. So you all know that it's better to go down directly. So this might be better. This is much faster, right? This is much faster than this one. That's why this might be better. Then how can you make this one? You will put discount factor here, which means that in each iteration, you will multiply gamma. So gamma is between 0 and 1. That's why they will reduce the Q value more and more when we have more and more iteration. That's why it would be better to achieve the goal in a faster manner. Okay, that's why by setting the discount factor in front of the Q value, you can accelerate the procedure to achieve the goal in the decision making. That's why this can be helpful for finding the optimal path here. But here, okay, so any questions up to here? Any questions up to here? So suppose that when you look at the one segmentation, this one becomes here. But here, if this one randomly choose this left-hand side, then this becomes 1. But here, if this one choose the downside randomly, then it will be 1. Then this path is much better. That's why this detouring is happening by taking the random action in this space. That's why in order to avoid these kinds of the detouring, you set the discount factor. That's what I want to say in this slide, okay? So this is one simple example about the Q running. This is one simple example about the Q running. This one shows the basic pseudocode about the Q running. And this one is how you can avoid some kinds of the non-optimality. So by doing the epsilon greedy, which means that you know that, so epsilon greedy is 0.1, which means that this is 10%, okay? So with the random, when you take the random value, that will be between 0 and 1, and with the 10%, you're gonna take the random action. Otherwise, you're gonna work based on your Q running. So with the 90%, you will work with the Q running. With the 10%, you will gonna take the random action in order to explore, maybe explore the search space nearby this one, in order to find maybe there is another better solution nearby there. So that's why we have these kinds of random action taking in order to find the better solution nearby the solution space. And initially, this one is 10% here, but when you're using decaying epsilon greedy, when you have more and more iteration, these kinds of the random chance is reducing more and more. That's why initially it has a lot of randomness at first, but when you have more and more iteration, you already found your optimal solution. That's why the chance for random access is reducing more and more. That's why this becomes reducing more and more by doing this for loop. That's why you will gonna do the reinforcement running or Q running action immediately as time goes by. Okay, this is called decaying epsilon greedy. This kind of randomness can be inside this Q values as well. Okay, so initially based on the optimal result, this is 43, this is 35, this is 41, this is 31. That's why this one will be taken because this is take the maximum reward. However, we are not making our decision only for Q. We consider the randomness as well. So by mixing some random values here, by adding random noise here, your this can be updated. That's why you can have this selection random matter, occasionally. That's why you can do some search nearby your optimal solution. That's why it would be some chance to look at the better solution nearby the optimal solution. Okay. And in addition to that, you can also do the decaying random noise because initially it's better to have the higher value in order to look at more aggressively. But as time goes by, you may already found your optimal solution. That's why the chance for looking at nearby space can be reduced. That's why you have decaying random noise as well here. Okay. And then you have Markov decision process definition here. So this one, Markov decision process, is very similar to Q-running. Everything is same, but it has only one more definition that is called transition function. Except this transition function, the others are all same with Q running. That's why it is very similar to Q running. That's what I want to say, okay? Okay, here. Then let me look at more details about this one, okay? So this is a state where the agent is playing here, okay? And then the S sub 0 means state, starting state, S means current state, S prime is our next state, S sub t means our state at time t. So this is a conventional definition for the variables. Those are using in our reinforcement learning formulation. And we have to define the action. This agent can go up, left, right, and down. That's why we have 4 different action taking. By taking some actions, this can move from S to S prime. So this is kind of the action taking at one space to the other space, okay? And that the other one is the reward. So this agent can move based on the reward. So if we have reward +1, then it has some chance to take this one. If the reward here is negative value, then we can avoid this space. By setting some reward here, you can design the trajectory of this agent, okay? And then here, how good was the choosing the action that is defined as the reward? And suppose that you are in S, by taking the action A, then you can move to S prime. Then that is called reward R. So reward can be -1 negative reward for moving if they are using battery, because it has more and more moving. It has some battery taking, battery consuming. That's why you have negative reward, which means that you have to achieve your goal in a small number of the actions. This is talking about that. And by taking this item, you may have some benefit. That's why this is positive reward. And when you exit, then you can escape from this game. That's why this is the maximum reward, what you can get. That's why you have these kinds of the reward setting in order to play on top of this maze. So lastly, this one is the one big difference from the Q running. So here, suppose that your agent here, you can go up, you can go left, you can go right. So this is your action taking. Go left can be realized with the probability of 0.1. Go up can be realized with the probability 0.8. Go right can be realized with the probability 0.1. That's why you can set separated or independent probability for individual action taking, right? So the T means transition probability, and this is the where is the robot's new location. So suppose that you are in S, suppose that you are taking the action A. These are given conditions, and then based on the given condition, suppose that the probability, suppose that you have to get the probability to go to S prime. That is called transition function, okay? So you can define the transition function just like that. We already studied about the discount factor. If we have more and more discount factor, then you have more and more discount of the reward value or values. That's why if you have almost 0 discount factor, then the discount will be available much more aggressively. Then you have to achieve your goal as fast as possible. If your discount factor is near 1, then you don't need to worry about that too much. That's why discount factor can control the speed of the convergence of the reinforcement learning problem. And then here, we already know what is the policy, right? So in earlier stages, we studied about what is the policy. So policy can be denoted by pi here, or that is the mapping with the state and action. So when you look at the right-hand side, in individual state, you are mapping the actions. So suppose that you are in this robot. This robot can go up, and based on this action, go right. Based on this one, go right. Based on this one, go right, 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 and down. Then you achieve the goal in a fastest manner. That's why this is your maybe optimal action or optimal policy, right? So policy is setting all the actions inside the state. So this one maps the states to actions. That's why, as you can see, right-hand side in individual state, you map your actions. That's why this is called policy. So given an action for every state. Okay, these are all have same meaning. And then your goal is that find the policy that maximizes expected return. Expected return can be denoted by this one, and this one is accumulating all the reward value with the discount factor. Okay, so that can be defined as the return value. That's why based on this return, and then you have to get set up the actions which can guarantee the maximum reward. Okay, that's what you have to do here. So state value action value function, this is your Q function, right? Q, and then you suppose that you are in S, suppose that you want to take the action, then your given conditions are state S and action A. Based on these given conditions, you have to take the reward. And this E means expectation. That's why you want to maximize this Q. That's why you are maximizing the Q value. That's why this is very similar to Q learning. Okay. Only one difference is that it makes the transition probability. So this one is only one difference between Markov decision process and Q learning, which means that in Markov decision process, you are defining the probability, transition function, transition probabilities, individual steps. There is only one difference here. So when you look at this one, you may think that Q learning is not optimal because this one is detouring. So this is better, but why this one is detouring? This is not optimal because they are taking the random action. Go left, go down, they are taking the random action. But here, this is not taking the random action, right? This is not taking the random action in Markov decision process. In Markov decision process, the action is taking based on the probability setting. That's why this is deterministic. In Q learning, you are taking the random action. That's why it's not optimal. But in Markov decision process, you are taking the action based on the transition function. That's why this one guarantees the optimal solution. Okay. That's why Markov decision process is one of the successful and famous algorithm in reinforcement learning in a conventional way. Okay. So in optimal action, so if the transition function values are all given, if reward values are all given, that's why this is planning problem. That's why, as I told you before, we can solve this problem with dynamic programming and we can find the optimal solution. Okay, that's why we can get into optimal value. This is very clear, right? That's why Markov decision process is one of the successful application in worldwide. And in textbook, in industrial engineering, when you study about the operation research, you're gonna study about the Markov decision process. This is quite well known even in undergraduate courses, okay? So from now on, you have some formal description about the Markov property, Markovian, and so forth, but everything is already explained before. That's why you don't need to worry about this one here. These are all explained here, okay? So now this is the thing what I shared before. So if you have any questions, please let me know. So did I share the other slide for our lecture for neural network based reinforcement learning? Did I share about that before? Can you answer about that? So did I share only this slide before? Hello. Let me check. Yeah, please. Maybe we have to get one more slide for neural network based reinforcement learning. So we have to study about that. Okay, yes, this is the one that I want to find. Okay. Okay, now I want to explain the deep reinforcement learning. So until 1990s or in the early of 2000, we have a lot of study about the Markov decision process. As we studied about before, that's fundamentally based on the dynamic programming. It can guarantee optimal solution, which is very good. Then what is the problem? The problem is that the computational complexity of dynamic programming. The computational complexity of the dynamic programming is pseudo polynomial, which is not polynomial. That means that if your state is very small, then you can get the optimal solution, no doubt, clear. But if you have a very complicated state, then it will gonna take a lot of time to make a computation. That's the main problem here. But nowadays, most of reinforcement learning problems are for AlphaGo or something like that. These are all very complicated states. That's why the computation with the Markov decision process is not possible based on the computational complexity. That's why we have to think about how can we deal with that kinds of problem. That's why in order to conduct faster computation, we start to think about the deep learning based reinforcement learning. Now the name becomes deep reinforcement learning, not pure reinforcement learning. So that is the main difference here. So nowadays there are a lot of research in reinforcement learning. So a lot of research in reinforcement learning is purely for the deep reinforcement learning, not MDP, right? So here, so let me go to the concept of the, but here, so I think that we have, I can share better slides with you that is much more clear to understand. So let me share one slide with you. This slide. This is better to understand. So this one, okay? So deep neural network, we have to understand what is a neural network at first, and then we can think about how can we design reinforcement learning inside the neural network. I will gonna share this one with you, just like that. Wait a minute, please. Here. And then, so you got this one, right? I share one PowerPoint slide with you. I will gonna make a lecture based on this file, okay? So this is neural network. Maybe you studied about neural network for a long time during your graduate, because to write technical papers, you need to understand what's the deep learning nowadays, because you are using a deep learning framework for many applications for your research. That's why you may understand what is the deep learning. So in deep neural network, this is the neural network. Neural network, you have hidden layers, you have outer layer, okay? You have hidden layer and you have outer layer, right? So that's why when you have one vector input here, this will go to the hidden layer. So when you go to hidden layer, this three-dimensional vector will be here. That's why three-dimensional vector will be here. And then this 1/3 matrix will be multiplied with 3/1. Then based on the linear combination in linear algebra, 1/3 multiplication 3/1 becomes one value. It will be aided with bias, and then it will gonna take the activation function. The return value becomes this one. And similar computation will be available here as well. So this 1/3 matrix will be here. That's why 3/1 matrix will be multiplied here. And then the result will be the one value that will be aided by this bias. And then by taking the activation function, this value becomes this one. For the third one, 1/3 vector will be here. And then this one has a similar 3/1 vector here. And then you are doing the matrix multiplication. Then the result will be the one value that will be aided by this bias. That's why this is one value. And by taking the activation function, the result will be the here. Similarly, the result is the here. And you have the one vector. But the vector size is 4, 1/4. That's why, next slide, you have 4/1 vector because your incoming is 1/4. That's why in order to do the linear combination, you have a 4/1 vector. That's why you are doing the linear combination, aiding this bias and taking the activation function and so forth. Then you have this 4 size vector. Similarly, in output layer, you have a 4/1 vector in order to the linear combination. And this kinds of the matrix multiplication procedure simply. The neural network computation is simply matrix multiplication multiple times, right? So when you look, so now then in order to explain the beauty of the use of neural network can be explained in interpolation theory in numerical analysis. So I think that it would be better. So because today we have only 1 hour lecture today, that's why we may finish here. That's why we have no enough time to explain neural network. But I hope that we have some makeup class because I'm laying 2 hours here. That's why in order to explain this one in English, I want to make a schedule with you guys for the other classes during this week. So here, let me ask when your available time during this week. So as you can see here, how about Friday? Are you available Friday afternoon? Then I want to have some makeup class here. So Friday afternoon, I have no classes at all. That's why if you want, we have 2 more hours for explanation of the reinforcement learning in English. That's why could you please pick 2 hours here? Then we can have a makeup class. So Julius, are you there? Julius, yeah, Julius, when is your available time on Friday here? Then we can have makeup class because we have only 1 hour today. That's why I want to have makeup class for 2 hours in order to explain neural network-based reinforcement learning. Could you please let me know when you will be available here? Two to 4. So are you guys okay with the 2 to 4? 2 to 4? Are you guys okay with that? Then we can have makeup class. Okay, Trin, 3 to 5. Then Julius, how about 3 to 5? No problem. Okay, that's good. Then thank you for your participation today. So today we studied about the Q-learning and Markov decision process. Those are conventional reinforcement learning algorithms which we can use in many applications. On Friday 3 to 5, we will gonna have a makeup class in order to explain deep learning based neural network architecture. I think that it would be enough with 1 hour. That's why maybe 3 to 4, I think. But if we have some more discussions or Q&A, then it would be 5, but most likely 3 to 4, okay? Thank you for your participation today. Let's meet all together, 3 to 4 or 405 here. So this is our makeup class. So this is our class, 3 to 4:30, maybe. 3 to 4 or 3 to 4:30. Maybe 1 hour would be enough for explaining neural network-based reinforcement learning. And thank you for your participation today. I will upload this video in our chatting room and Blackboard. Then you can review what we have studied up to now. Then based on that, we will gonna meet all together on Friday, okay? Thank you very much for your participation today. We're gonna meet all together on Friday. Thank you. Thank you.